In this lesson, we will apply the concepts that we have developed until now to different situations of open channel flows as listed here. Let us start with Venturi flumes, illustrated on these pictures. These are special devices with a particular shape, as we can see, that feature a local narrowing of the cross-section, which means a sequence of a narrowing followed by a widening. Venturi flumes are used to measure the discharge in small streams by measuring the water depth at one or two locations, as we will see. To describe the flow in such a device, we will assume a horizontal bed, which is almost always the case in practice. We will neglect the friction forces and consider that the head losses in the converging and diverging parts are very limited. Indeed, the converging part AB is often designed with an elliptical shape to avoid the flow contraction L2 that is illustrated here. Here, of course, with a straight line, we don't have a very nice design. Besides, the divergent section is very progressive to avoid a flow detachment that would lead to significant head losses. We will first consider the submerged case. That happens when the ratio L2 over L1 is not too small. Using the specific energy diagram, we can describe the water profile as follows. We assume a uniform flow upstream here and downstream of the flume, in such a way that the starting point and the arrival point are both U1 here. The passage on the specific energy curve corresponding to L2 is very short. It is represented here by one single point, point 2, as the narrow part of the flume is short. So, to reach point 2 on the L2 curve, the flow has to gain first some specific energy until point 1. Point 1, which is here at the beginning of the converging part. This is achieved by a M1 profile. Then, the flow depth decreases until point 2, and finally slowly increases again in the widening part to come back to U1. The two specific points of interest are point 1 and point 2. Point 1 is the highest water depth, and point 2 is the lowest point. Writing the Bernoulli equation between these 2 points will allow us to determine the discharge. Looking at the specific energy diagram for these 2 points, 1 and 2, we can see that the velocity at point 1 is much smaller than the velocity at point 2, where the flow accelerates. Therefore, considering that V1 is much smaller than V2, we can neglect V1 square over 2g and write equation 2, in which we have expressed the velocity V2 in terms of the discharge. Remember, the cross-section is rectangular. Finally, rearranging the terms, we obtain equation 3 that allows to deduce the discharge from the simple measurement of the water depth at point 1 and at point 2. Of course, such a device in practice should be calibrated, and a discharge coefficient μ is added in the final formulation in order to account for the head losses, the possible bed slope, the exact location of the two measurement points, the two measurement devices, and the way the measurements are taken. If the ratio L2 over L1 decreases, we obtain the situation illustrated here, in which the flow widening becomes too important, and as a result, a hydraulic jump occurs in the Venturi flume. Contrarily to the submerged case, we now have a flow that goes below the critical depth here, and this is why this situation is called the unsubmerged case. As in the previous case, we start from U1 and arrive at U1. But now, after increasing with an M1 water profile, the water depth decreases in the converging part until reaching the critical depth at point C2, point 2 here. Then it further decreases below HC1 until point 3. So we then have a short M3 profile from point 3 in the white part of the channel until point 4, where we have the hydraulic jump that connects the M3 profile with the uniform flow U1. We could apply the same procedure as before by measuring H1 and H2. However, in the present case, we know that H2 corresponds to the critical depth here at point 2. So, as we have assumed a horizontal bed and negligible head losses, we can consider that the specific energy E1 at point 1 is equal to the specific energy E2 at point 2. Again, looking at the specific energy diagram, we can see that the velocity at point 1 is negligible, in such a way that E1 can be written as in equation 2 here. E2 is in fact equal to EC2, the specific energy at the critical depth HC2. And as the cross-section is rectangular, we can write E2 or EC2 as 3/2 of HC2 or H2. So, combining equation 1, 2, and 3, we can write this equality here in equation 4. This allows to rewrite the discharge expression 5 that we obtained in the previous case, in the submerged case, as in equation 6 as a function of H1 only. And here the coefficient is simply calculated from the different constant values. So such a device with an unsubmerged flow allows to measure the discharge with only one water depth measurement. And it is therefore, in general, the preferred option if a hydraulic jump is acceptable, of course. In practice, the geometry of the flume is normalized. One of the most popular normalized geometry is the Parshall flume, in which the bed profile is adapted, as we see here, to force the position of the hydraulic jump in the narrow section. The water depth measurement is taken here in the converging section. Such a Parshall flume is installed at the outlet of the lake of Louvain-la-Neuve to measure the discharge that flows out of the lake into the Malaise River. Another application of flow contraction is the flow between bridge piers. This contraction might appear as negligible in some cases, but in some other cases, these bridge piers can reduce significantly the river width. We will analyze this situation based on this sketch, considering a pair of bridge piers at a distance L1 from each other, and a local narrowing L2, with an additional contraction mu L2 if the design of the piers is such that it induces a local flow detachment. The situation is similar to the one analyzed just before for the Venturi flumes. We consider here a circular bridge pier, which means that the narrow section L2 reduces to a single point, here at the widest part of the bridge pier. We have a uniform flow upstream and downstream, which means that the starting point and the arrival point are U1. The flow depth first increases with the M1 profile until point 1, then decreases until point 2 on the L2 specific energy curve, and finally increases again to HU1. In the same way as for the Venturi flume, a hydraulic jump can occur if the ratio mu L2 over L1 becomes too small, which means, in fact, a strong reduction is in the space available for the flow. In this case, the specific energy at U1 is lower than the specific energy at C2, in fact, too low for allowing a direct connection between C2 and U1. So, the flow first increases its specific energy by increasing the water depth through a M1 profile until point 1. Then, at C2, it is impossible to return directly to U1. So, the point representative of the flow goes to the left branch of the L1 specific energy curve in order to lose enough energy. As a consequence, the water depth further decreases and reaches the L1 specific energy curve at point 3, below the critical depth. This can be seen here, an increase of the water depth until point 1, a decrease, a passage through C2, and a further decrease until point 3. From this point, a M3 profile starts until a hydraulic jump that allows to return to U1. However, it must be kept in mind that such a situation is often not acceptable in practice, because this hydraulic jump and the associated energy dissipation might damage the foundations of the bridge piers. It is very close to the bridge piers and it induces a lot of turbulence and roller effects, as we have seen. Moreover, it is clear that such a jump is prohibited in a navigation channel. In any case, we have seen that the flow starts with a M1 profile, if it's here without hydraulic jump or with hydraulic jump, because the flow first needs to increase the water depth until point 1, together with an increase of the specific energy. This backwater effect is important to know in practice, because, as we can see, it can have an influence over a quite long distance upstream from the bridge pier. The detailed calculation of H1 is complex, as it would require a perfect knowledge of the flow and drag coefficients of the bridge piers. In practice, empirical formulations such as the one proposed by Rebock are allowed to estimate the depth H1 and thus this backwater effect. In Rebock's formula, the coefficient here, μr, depends on the shape of the bridge pier, rectangular or rounded, and its value can be found in graphics such as the one given here. Over steep slopes, two different behaviors can also be observed. The first one is illustrated here and corresponds to a limited obstruction. Upstream of the bridge pier, we can only have a SU profile. Then, the decrease in specific energy to reach point 2, so from U1 to point 2 here, induces an increase of the water depth. Specific energy further decreases along the bridge pier, and finally, when arriving again on the L1 specific energy curve at point 3, a S2 profile develops to reach U1 again. When the obstruction becomes too large, we observe the formation of a hydraulic jump, as illustrated here. This occurs when the specific energy at point U1, so here, is not sufficient to reach the lowest possible specific energy on the L2 curve, that is point C2. So a hydraulic jump first forms, followed by a S1 profile that allows to gain enough specific energy for a smooth transition across the critical depth until point 3. And from this point, a S3 profile allows to come back to U1. So this is illustrated here. Uniform flow, hydraulic jump, S1 profile, a decrease of the depth along the bridge pier until point 3, and a S3 profile. Let us now describe bottom sills. Bottom sills are other types of singularities that can be described using the open channel flow theory. Such bottom sills can be natural or man-made to prevent riverbed erosion, for example. Depending on the flow regime, sub or supercritical, two different behaviors can be observed. Let us start with the case of a subcritical flow, with a flow depth larger than hc. We assume that the increase here in bed elevation is sufficiently smooth to induce no significant head loss. Therefore, the energy grade line can be assumed as horizontal. If we represent the two specific energy curves as done here, each taking its origin at its bed level, the two curves represent in fact the total head and not only the specific energy, as we can see from the equation here. And if the channel is rectangular and prismatic, the two curves upstream and downstream from the bottom sill are identical. So we have exactly the same shape, but just shifted vertically by the height of the sill. So if we have a water depth h1 before the bottom sill, with an energy level indicated by point A here, the corresponding energy level after the bottom sill is represented by point B, so the same total energy as we have assumed no head losses. This leads to a water depth h2 smaller than h1 and a flow that accelerates, as the kinetic energy represented by the distance b prime here is larger than the kinetic energy a prime. This result might appear as surprising. A rising bottom implies a depression of the water profile. In fact, this can be explained by the need to use a part of the energy to accelerate the flow over the obstacle. In the case of a supercritical flow, a similar analysis conducts to the conclusion that the flow decelerates and the water depth increases over the bottom sill. This observation will allow us to analyze the broad-crested weir. As indicated by its name, the crest has a significant thickness that will affect the flow. Looking at this image, we can recognize on the upstream side the typical flow shape over a bottom sill that we just analyzed, with the decrease of the water depth. On the downstream side of the weir, we have a free spill, and thus typically a critical depth here. We can also see on the pictures that such weirs have a rectangular cross-section, as most of the weirs in practice in fact. So let us describe the situation. Equation 1 is the equation of the critical depth for a rectangular cross-section. For such a cross-section, we also know that the specific energy EC is 3/2 of the critical depth HC. Combining equations 1 and 2, we can write the discharge as in equation 3 here. Then, assuming that the velocity in the reservoir is negligible compared to the velocity on the weir itself, we can replace EC with the depth h in the reservoir. So here the small kinetic energy can be neglected in such a way that we can consider that EC is equal to h. Of course, h measured from the crest level. And this coefficient 0.385 is simply the value obtained after calculating the values of the constants in equation 3. In practice, the discharge coefficient denoted here by mu will take slightly different values as indicated here in equation 5. It must be noted that such a broad-crested weir has a very poor efficiency in terms of discharge evacuation. So in this lesson, we have applied the different theoretical concepts that we have discovered so far to analyze some specific applications. The analysis is most of the time conducted using the specific energy diagram, complemented with the knowledge of the different water profiles. And with this, we finish the series of lessons devoted to open channel flows. I hope you enjoyed it. Goodbye.